last time I stopped at the introduction to special relativity, where we talked about the discrepancy between classical dynamics, where if you normally add speeds. If you're running and you throw a ball, then the speed of the ball is v plus u. If you're running at a speed u and you throw the ball at a speed v. So this is classical dynamics. And then I pointed out the contradiction in electrodynamics, which means that if you're standing still and you launch a flashlight at speed c, and then you run at a speed u and again launch the flashlight at speed c, then according to the laws of electricity and magnetism, you should an observer on the ground will still measure the speed c, even though you're running. Okay? And this contradiction between classical dynamics and electrodynamics, the fact that they give different answers, this is what led Einstein to the special theory of relativity. And so we'll explain how Einstein went from there to the special theory. But in the beginning now, before I get there, I want to concentrate on what I call the laws of electricity and magnetism, and how the laws of electricity and magnetism lead to this conclusion that the speed of light is a number. And the number comes out of the theory of electricity and magnetism. So that if the plane is flying at a speed c, the pilot inside the plane, if somebody sends him a signal from, say, the air control tower, if he sends him a signal at speed c, he will if he sends him a light beam, he will measure the speed of this light beam to c, even if the plane is flying at 500 miles per hour. And if he's on the ground, he will also measure the speed of the light beam to be c when he's standing still. Okay, so almost the same thing as pouring a glass of wine, and the glass of wine looks the same. So we get that because the speed of light is, this number is a law of electricity and magnetism. Now what Einstein did, and now this is the introduction to Einstein, what Einstein did was he said, in order for two moving observers to obtain the same speed of light, they must use different time and distance measurements. The clocks of moving observers are different from the clocks of stationary observers, and the rulers of moving observers are also different. Now it's not just that the ruler contracts, okay? It's just that space itself changes. And it's not that the clock mechanism changes, it's the notion of time itself that changes, okay? So it's the fundamental aspect of time. And the reason he did that was because he knew that speed equals distance interval over time interval, and in order to get the same speed for a moving observer and for a observer at rest, he will have to change distance and time. And that was the idea. So space and time are not the same for all observers, which really contradicts our inbred belief that space and time are the same for everyone. Now, this theory of relativity also changes another inbred belief up to that time, that electricity and magnetism are two different phenomena. And what his theory showed is that electricity and magnetism are really one and the same phenomena. Okay? And that's really strange, and you'll see how strange that is. But it's a natural consequence that comes out of this theory. All right. So as you know, Einstein was declared to be the person of the century, 1900 to 2000. You know, the Time magazine interviewed many famous people and reporters and scientists and so on, and politicians, and they came up with votes of who is the most important person, who had the most influence on our culture over the 100 years from 1900 to 2000. And the vote was heavily in favor of Einstein, so they made him the person of the century. You know, normally they have the person of the year, so he was the person of the century. Does anybody know during this poll who was the runner-up? Who? Kepler. Did you say Kepler? No, Kepler was like 4 centuries earlier, yeah? 4 centuries earlier. And they would probably not choose another scientist, okay? But who, in your mind, who had the most influence on the culture or the events of this world for 100 years, over the 100-year period? Any guesses? Who? Yeah, you got it. Gandhi. Right. Mohandas Gandhi was chosen to be the next person. All right. So that's the electromagnetic wave, all right? Of course, it's just a mathematical construct that I'm showing you now. It's the electromagnetic wave. But what's waving here is these red arrows and these blue arrows, okay? And these red arrows and blue arrows, really, they show you this is the magnetic wave, magnetic field wave, and this is the electric field wave. And these two waves are coupled together, and they wave together, and the entire electromagnetic wave then propagates in this direction as the electric and magnetic fields, as the electric and magnetic arrows move up and down in this waveform. Okay? So that's really what we mean when we say electromagnetic wave. I'm going to pause here for a second and make a little connection for you to what Einstein observed. Right? The moving charge is magnetism, and the moving magnet is electricity. And you know, Einstein was very fond of making observations that, you know, physical phenomena are the same, even if you are in different frames of reference. As I explained to you last time when I was on that cart, and I showed you the ball and the trajectory of the ball. So last time I showed you this nice this demonstration, I think it's this one here, that you could move a ball up and down and have a vertical motion, or if you're on a truck, you'll have the parabolic motion. And Einstein thought about this business about electric charge, and he said, suppose instead of a ball, this guy was holding a charge in his hand, right? He charged it up, his hair's flying out and all that, okay? He's holding a charge in his hand. And he will say, I see a charge, okay? And now, suppose that he starts moving in his truck. Then instead of a charge, okay, now the guy on the ground, here will see a charge, but when this is moving, the guy inside will still see that, will still be in this position, and he will still say, I see a charge, okay? I see a charge. But this guy on the ground will see a moving charge, okay? And the moving charge was the same experiment I did over here, and the moving charge is a magnet. So you see, the guy on the ground says, hey, you got a magnet, and the guy in the truck says, I got an electric charge. So just like you have a straight path and a parabolic path, they're the same things. Same way, electricity and magnetism are two facets of the same thing. It's just that in one case, you're moving. Right? So that was Einstein. So that was Einstein's great discovery, that electricity and magnetism are the same. We just have different frames of reference. Now, come to the final experiment, and this is going to be a simulation. No, not really. I'm going to do a simulation first and then an experiment, where we come to this guy Maxwell, who said, moving charge, electric current, produces magnetism. Moving magnetism produces electricity. Electricity and magnetism are one and the same thing. And he calculated from these electric and magnetic fields, he calculated what should happen if you have a plus and a minus charge constantly moving back and forth. And I'm going to visualize that for you with this very nice tool. It's a mathematical tool. It's a mathematical simulation where I have a positive charge here, okay? And what I'm going to do is I'm going to grab this positive charge and move it up and down. But instead of actually physically moving the charge up and down, I'm going to do it on the computer, and I'm going to use the equations of electricity and magnetism to generate what happens to the electric and magnetic fields when you move a charge. Actually, I'm going to use Maxwell's equations. But I'm not going to bore you with all those equations, okay? So I'm going to just show you physically what happens if I grab this charge and slowly move it here, all right? So of course, when I move the charge from here to here, I disturbed the electric and the magnetic field a little bit, but then it settled down because the charge came to rest. But while the charge was moving, it was an electric current. And the electric field was changing, and the changing electric field changed the magnetic field. And then the changing magnetic field changed the electric field. And that's what makes the wave. The changing electric field makes the changing magnetic field. The changing magnetic field changes the electric field. And that's the wave. That's the electromagnetic wave. So here it is. I'm going to constantly change the charge. Going to constantly change the charge for you, up and down. Okay, and I'm going to generate the electromagnetic waves of Maxwell. All right? And so these wave fronts that you see out here, okay, these are like your ripples in a pond, and these, when they go very far out, are your plane waves that you saw with my vectors before for the first movie. So that is the conclusion that Maxwell came to is that if you move electric and magnetic charges, one effect will create another effect, and the other one will work backwards and create back the electric field and magnetic field and back and forth. And then he came with this remarkable realization that he could solve the equations of electricity and magnetism, which I won't show you. But the most important conclusion that he reached for us is that he could calculate the speed at which that wave propagates, okay? Because he knew the equations with which electricity changes into magnetism and vice versa. And he determined that that speed, he actually determined a number for that speed, That number was 3 times 10 to the 8 meters per second. So just by using the laws of electricity and magnetism, he determined the speed of light. He says, I have an electromagnetic theory of light. So he was the first person to show that light is really the same as electromagnetic waves. But again, to review, the laws of electricity and magnetism are the same for the flying plane as for the pilot who is standing still. And we're going to show you how Einstein changed space and he changed time to get the same answer for the velocity of light, okay, which you now figured out how to use that. Okay, which you now figured out how to use that. But I'm going to simplify things for you a little bit, okay? So that's Einstein simplified. All right. So here is what he came up with. Okay, he said that suppose you have a train that's moving, right? Suppose you have a train that's moving, and instead of a clock, instead of a mechanical clock, I'm going to use a light clock, okay? And a light clock is something that you have a light beam that goes up and down. So instead of a ball falling up and down, and you're measuring the time that it takes the ball to go up and down, we're going to have a light beam that goes up and down, okay? Now, the guy on the train has a clock, and he's going to measure. This is a very difficult experiment, but let's suppose in your imagination that he can actually measure how long it takes the light to go up and down, okay? And the guy on the ground is also going to measure how long it takes the light to go up and down, except that the guy on the ground will see the train moving, okay? So this guy will see the train moving. Now you know that the guy inside the train doesn't really know the train is moving, right? He just sees the ball going up and down, he sees the light beam going up and down, and for him it will take so much time, okay? But the guy on the ground will see the train moving and the light beam going up and down, and so the path of the light beam really is not this path, but it's this path. Follow? Which means that the light will take longer to go from here to there. And so his clock will read more time. So for the same event, namely the light beam going up and down, the guy on the train says it took 1 second, and the guy on the ground says it took 10 seconds, because it has to travel this much. Now it doesn't go any faster, right? The point is the light goes at the same speed. So let me try to make you a nice movie about how these two separate clocks will work. Okay, so here we go. Here are the two different clocks. Okay, but you'll notice for many clicks of the clock on the ground, the one in the train is making only 1 click. Right? So that means it takes more time in terms of the clock on the ground compared to the clock on the train. Right? Now you can use that. Now you can use that the connection between the time on the train and the time on the ground. There is a connection between this clock, and that's this formula. So this, if delta t prime describes the clock on the train and delta t the clock on the ground, this is the connection. And I'm actually going to derive that for you. Okay, so now look, this distance here, if the time on the train is delta t prime, then this distance is just c times delta t prime, using the same equation that you just used to calculate distance and time and speed. All right, so that's c delta t prime. This distance here will be c delta t, because this is the time delta t. Delta t is the time on the ground, okay? And the distance that the train has traveled will be v delta t. C delta t, C delta t prime, C delta t, and V delta t. I'm going to take these three lines and put them on the next picture. Okay? So there's C delta t prime, there's V delta t, there's C delta t. Okay? And notice that I can connect them into a right angle triangle and go back to my good friend Pythagoras. All right? And connect these three quantities with Pythagoras' theorem. C delta t squared by hypotenuse equals V delta t squared plus C delta t prime squared. And that will give me the connection between delta t prime and delta t. All right, first I move this, I move all the delta t's together on one side and the delta t primes together on the other side. And then I open up the brackets, so I get C squared delta t squared minus V squared delta t squared equals C squared delta t prime squared. Then I collect C squared minus V squared together, delta equals C squared delta t prime squared. And now I divide the whole equation by C squared. Okay? If I divide the whole equation by C squared, I can say this C squared and this C squared give me 1. This gives me 1 minus V squared over C squared. So delta C squared and delta t prime squared are now connected by this famous equation that I wrote down before. Delta t prime equals delta t divided by square root of 1 minus V squared over C squared. Okay? Now that turns out to be a very important equation. It's called the equation of time dilation. Okay? And it connects the two clocks together. It tells you how much faster and slower the moving clock is going. So when you're moving on a spaceship, your clock's going slower, and so if you come back, you're younger, right? Because your clock's going slower. All time for you is slowed down, okay? Relative to the guy on the ground. All right. Now there's a similar connection for the rulers. See, the rulers of the moving train look shorter than for the guy on the train. And I'm not going to derive this, but there's the connection between the moving ruler and the stationary ruler. So space is deformed in the same way. So if you happen to be on a spaceship and you're flying over a football field, okay, if you were not moving and you parked a Goodyear balloon on top of the football field, you will see this. But instead of in a Goodyear balloon, if you're in a spaceship moving very fast and you take a snapshot of the football field when you arrive on top of the football field, your snapshot will look like that. Okay? The space will be distorted for you. In other words, the whole football field is moving past you, and it'll look like that. So that's the basic idea of relativity. So now we can ask the question that we asked before when we had the ball moving up and down and we had the ball taking a parabolic path. We can ask the question, who has the right clock? Like, who has the right path? Is it up and down, or is it a parabola? Who's looking at the right thing? Is it electricity, or is it magnetism? Who has the correct distance? And the answer, as you know, is they're both right. There is no unique observer and no unique frame of reference. Okay? And later on, in just about one slide, I'll give you an analogy. Okay? And this equivalence of reality for different frames of reference, this equivalence of reality is really something that the artists of the time also recognized on their own. Okay? So I'm going to pretend that I'm Picasso. All right? I'm going to do a work of modern art in front of you. Right? So what I did was I took a digital camera and I took a fruit bowl. Right? And then I took a digital camera picture of this fruit bowl, which is full of bananas and oranges and so on, from the short side. Okay? So here's one perspective of reality from the short side. Then I turned around and I took a picture of the fruit bowl from the top. And you notice that it looks totally different, but it's the same fruit bowl. Right? So these two visions of reality are just two perspectives from different points of view. Now here, these are really different physical, spatial points of view. Okay? Not different frames of reference. And then I turned around and took the same fruit bowl from the long side. Okay? Okay, so I took it from the long side. Now, if I was a Picasso, I'd say that none of these perspectives are satisfactory, because reality is all of them. Right? So what I'm going to do is, guided by Picasso, I'm going to combine the top and the long side, and give you a modern art view of the fruit bowl. And then I'm going to combine the other one, all three of them. And there's my fruit bowl, okay? This is my Picasso fruit bowl for you, okay? So I call it modern still life, okay? So all three pictures imposed. Now this is exactly what Picasso was doing, right? And I'm going to show you. This is Picasso, right? So he's got portrait of Marie Therese, okay? So if you look at the hat indicates the eye level. But the face has several different viewpoints which he juxtaposed together, like I did the fruit bowl. So the face has eyes. One viewpoint is the eye, another viewpoint for the mouth, another viewpoint for the nose. And then when he juxtaposed together, he got this, okay? Which everybody stares at and says, wow, Picasso's a genius, okay? So all he's doing is taking three different perspectives and combining them in a fluid way. Similarly, the floor, well, the chair has two different points of view that she's sitting on, and so on. So it's a real coincidence, but I think it's sort of typical that as our cultural thinking changes, that we're willing to accept different points of view as real, all of them equivalent, the same thing was happening in physics as happening in art. Now, if you can read books about Picasso, okay, and it turns out Picasso knew nothing about Einstein. And if you asked it, Einstein was actually asked this during an interview, is that, did you know that Picasso was doing all these things? And he said, I had no idea that Picasso had, was doing similar things in his paintings. All right. Now, I keep telling you about this twin paradox. So let me go through this twin paradox again with you more systematically. The twin paradox is that, this is true, you can travel into the future of your own twin. Right? What does that mean? So you've got two guys, Tim Young and Jim Young, and they're twins. And one guy gets on a spaceship and takes off, right? And he goes to Jupiter or whatever faraway star, let's say Sirius, and he comes back. And he comes out of the spaceship, and he shakes the hand of Jim. And this is what Jim looks like. Yeah, Jim looked like this before, and now he looks old. 50 years have passed. But this fellow, only 5 years have passed. Okay? So this is not a paradox. Okay, this is real. This is what can happen. Okay. Now, what's the paradox is the following. The paradox is that you could think that Tim on the spaceship could think, I'm not moving. The Earth is moving away and coming back. And therefore, Jim should be younger than me. That's the paradox. Why is Tim younger and not Jim? Because from their different points of view, each other guy should say you should be younger. And the answer turns out to be that it's Tim who will be younger. Okay? And the reason is that it is possible to tell who's moving, in this case, and who's not moving. Because in order to go to Sirius, he has to accelerate. And when he accelerates, he falls back. Okay? And time changes for that also. Right? And then, in order to turn around, he has to come to a stop. And time changes there also. And in order to come back, he has to turn around and accelerate. And the guy on Earth is not doing any of these accelerations. Okay? So you can tell between the two people who is really moving and who is not moving, because the guy who is accelerating and decelerating to turn around and come back is the guy who is moving, and therefore he's the younger guy. And as it turns out, he is younger more because of his accelerations than because of his moving in the at long speeds. He's also younger because of that. And we will see that when we do general relativity at the end of the course, that most of his age difference is because he's accelerating and decelerating.